In this video, we're going to focus on what we mean when we discuss complementary events and we're talking about probabilities, okay? So complementary events, let's go ahead and start by defining it. We say given an event A, the event A prime, that's how you read this little comma here, apostrophe, A prime is the set of all outcomes that are defined as being not in A. So we say two events, A and A prime, are complementary. We could actually illustrate this if we were to say, well, okay, we have the set of all events here. We could say, all right, let's let this on the left here represent all of the outcomes in some event A. So perhaps, you know, like getting a red card, that would be all of the things in here. We would define A prime as being the set of all things that are not in A. So we could look at it this way. As a matter of fact, we wouldn't even have to partition the entire sample space here this way. We could say, let's just call this A. Right here, you know, if this represents the event A occurring, we would say everything on the outside here would represent A prime. So the definition of A prime, or the complement of A, would be A prime, and we'd say it's simply whatever A is, these are not that. They are the exact opposite. So just as an example of like what would be like complementary events, we could say, well, I don't know, red cards and black cards in a standard deck of 52 cards. The event that you get a red card and the event that you get a black card are complementary. The reason being is because if you were to look at a deck of cards, we could say, well, I don't know, I mean, like we've got all the red ones over here, red and black. But if I said, well, how likely is it that I get a red card? I think that we get like a 50% chance. But then if I said, well, I don't know, what if you wanted to get a black card? You know, we could just say, well, it's everything but red. That would be the same thing as getting anything but red. So we could say, let's take the whole space here, which is 100% of our stuff, and let's subtract off the 50% that's red, and it should leave behind this other portion right here. Okay, other complementary events include this, like even numbers and odd numbers on a standard 6-number queue. You talk about number queues a lot with probability, but if you were to consider complements, you know, here's our number queue. We could draw out what we see. We say we have a 1, doesn't go in this order, 2, a 3, a 4, a 5, and a 6. We'd say, okay, well, let's consider this. All of the odd numbers would be 1, 3, and 5. So what if I said not odd? Well, that would be anything that is even. So we'd say if A is the event of getting an odd number, A prime would consist of all of these that are even. Or in other words, everything that is not odd, okay? And then we say days of the week and weekend days. Those are complementary because when I say, well, if the event here is a day of the week, what would be the complement of A, you know, the complement of the day of the week? In other words, what's everything but a day of the week? That would have to be a weekend day, okay? So complementary events are unique in the fact that if you were to say, okay, well, if, for example, the red card, black card example, we'd say, well, red cards, what's the complement to being red? Everything but red, which happens to be black. They should constitute the entire sample space here, or the entire space. So going back up over here on the right, we say any event A, if you were to consider it alongside everything but A, the simple fact is this: if you were to add them up, like the probability of getting something in A, so that'd be like this out of the total amount of space, and you were to add that to the probability of everything but A, which would be, you know, everything out here. If you were to add those two probabilities up, what you see is you should be coloring in the entire space here. So you get 1, essentially. You get 100% of your stuff. Okay, so this is such a unique fact that we can set up the following relationship. It says the probability of a complement of an event. It says the probability of the complement of an event A is the probability of A prime, but we define this as being 1 minus the probability of A. And where we're getting this from is exactly over here with this relationship. If the probability of A plus the probability of everything but A equals 1, then if we wanted to say solve for this, we could subtract from both sides. We could subtract the probability of A, subtract this number, minus the probability of A. And so we're getting this relationship that says if you want to find the probability of everything but a specific event happening, what we'll do is we'll take 1, which is 100%, and subtract off the probability that it does actually happen, and that should leave behind the probability that it doesn't happen. Okay? So like as an example of how this relationship would work, it's kind of like this. We say, well, let's find the probability that A doesn't happen. So let's say, for instance, somebody says, well, the likelihood of some event happening is about a 72% chance. We say, well, then I want you to go find the probability that anything but this happens. The thing is, we're saying if we were to look at this as an illustration, we would say A. You know, I say A. You know, here's the event A. and we say A has a 0.72% chance of occurring. So let's go find the probability that it's anything but A. All of this stuff out here. And what we know is, well, this plus the 0.72 has to add up to be one whole total thing, 100% of our stuff. So what we can do is this. We say, well, then it's 1 minus the probability that it does actually occur. In other words, the probability that anything but A happens is 1 minus the probability of A, which we've been given as 0.72. So we just go ahead and insert the 0.72 in here. We get this. So the probability anything but A happens is 100 minus 72% would leave us behind 0.28. 0.28. So it's kind of a silly thing to say here, but I mean, think about it this way. If there's like a, say, complementary events, like maybe it's a 72% chance that it's going to rain, then what's the chance it's not going to rain or anything but rain is going to happen? It'd be the other 28% that existed, okay? So for these next two, you know, it's just like saying, well, hey, if there's a 2/3 chance that something, an event A is going to happen, what's the probability that not A happens or anything but A happens? So we'd say 1 minus that 2/3, it leaves behind the other 1/3, okay? So if there's a 2/3% chance that A does happen, then there's the other 1/3% chance that A, as a matter of fact, anything but A, not A, happens. And last but not least here, you know, the thing is, we can use this relationship here, this formula, and that's what we should be doing, but you can honestly have a conversation about this. If there's like a 21% chance that A occurs, what's the probability that A doesn't occur? And so we'd have to say, well, 100% minus the 21% here leaves behind 79%. But again, this relationship all comes from this little ditty up top here where we say the probability that not A happens is 1 minus the probability that it does happen. And so we say the probability of anything but A happening here in this instance was 100% minus 21%. And it says, okay, well, then the probability that anything but A happens should be the other 79%. Okay, so why do we discuss complementary events other than the fact that we just like to know everything there is to know about probability? Well, I'll tell you what, it's sometimes a lot more convenient to use the concept of a complementary event when we calculate probabilities. And I've got a couple really good examples right here. So let's consider this. We say when two 6-sided dice are tossed, there are 36 total possibilities. And what I've done is I've drawn in, or not drawn in, but provided us with a diagram here of the different possibilities. What I want to do, though, is find the probability that, say we roll 2 dice and we get a sum, but that is not 8. Okay. So when you think of complementary events, you know, we say we have an event A. When we write A prime, we could also interpret this as meaning not A, anything but A. Okay. So when we say not A, we say the sum is not 8. It's like saying we roll 2 numbers here, and it's not a, say, a 2 and a 6, which would, you know, add up to be an 8. Or like a, you know, we'd have a 3 and a 5, or a 4 and a 4, or a 3 and a 5, or a 2, you know, 2 and 6. You know, we could go through here and we say, all right, well, if I want to find the probability that it's not 8, let's start with this. We say probability not 8. Okay. The way we suggest we should write this here is this: probability of 8 prime. In other words, anything but 8. And what we know is this: it's 1 minus the probability that it actually is 8. I want you to consider this. If we had to go through and count up all the things that don't add up to 8, well, 1 and 1's not 8, 2 and 1's not 8, 3 and 1's not 8, this isn't 8, this isn't 8, this isn't 8. You know, we're going to be sitting here for a while. It is actually a lot easier to say, well, let's find out how many things do add up to 8. And so we had mentioned like a 6 and a 2 adds up to 8. Or 5 and a 3 add up to 8, or 4 and 4 add up to 8, or 3 and 5 add up to 8, and we say 2 and 6 add up to 8. So in order to calculate this probability, it's actually a lot easier to say, well, look, if there are 36 total ways to do this, and I want the probability that it's not any of these red ones, what we could do is we'd say, well, there are 5 red ones. If there are 36 total things, why don't we just take off the 5 red ones, and it leaves us behind the other 36 minus 5, 31 things. So to write out how this would look over here, we say, well, then the probability of 8 prime, or anything but 8, would be this 1 minus the probability that it is 8. And so we say, well, what is the probability that we get a sum of 8? Well, we had 5 things that came out to be a sum of 8 out of 36 total things. So, you know, I'll do my work down here. We say 1 minus 5 out of 36. That's the same thing as with the common denominator 36 out of 36 minus the 5 out of 36. In other words, we're saying it would be the entire space, and we would take off the ones that did add up to 8, leaving behind the other 31 out of 36, which would have been anything but these red ones right here. Okay, so let's try this again. We say, well, let's go find the probability that when we add the two dice together, we get a sum that is greater than or equal to 4. So we'd write this way. We say probability that the sum is greater than or equal to 4. So here's what we could do. We could just say, well, I know there's 36 total ways to do this. Let's go add up all the ones that have a sum of 4 or bigger. Well, I want you to consider this. That's a lot of things. Like this is 4 or bigger. These would have to 4 bigger. These would have to 4 bigger, 4 bigger, 4 bigger, 4 bigger. You've got a lot of things adding up to be 4 or bigger. So here's what we'll do is this. Instead of doing that, we'll say, well, the probability that the sum is greater than or equal to 4 would be 1 minus the probability that the sum greater than or equal to 4 prime. In other words, everything but a sum greater than or equal to 4. As a matter of fact, we could actually re-scribble this one here as we say, well, what's the opposite of a sum being bigger than or equal to 4? We could say the probability that it's less than 4. And so let's go find all the ones that are less than 4. We say, what is the likelihood that I get something that adds up to be less than 4? And that would be, let's see, 1 and 1 is 2. That's less than 4. These add up to be less than 4. These would add up to be less than 4. As a matter of fact, these are the only 3 possible outcomes that would add up to be less than 4. It's a lot easier to just count those. So we'd say, well, the whole thing minus the 3 that are less than 4 out of 36, which is 36 36th, minus 36, or sorry, 3 36th, got carried away there. It leaves behind the other 33 36th. But consider this, what we were trying to find in the first place is that the probability of the sum on 2 dice would be greater than or equal to 4. All we had to do was this. Let's take off the ones that are less than 4 from the total amount, and it leaves us behind the ones that are greater than or equal to 4. So, this is kind of a really nifty thing to have in your back pocket when you deal with complementary events.